Yeah, so good morning everyone. It's my real pleasure to welcome you again to this series of webinars on Spintronics, what we call as WTS. So my co-convener Dr. Brajbhushan Singh is probably ill. He is not here, but on behalf of our team, we all welcome you. And today we have a very young colleague, Dr. Arnab Bose, whom we know from some time. Arnab did his PhD with Professor Ashwintula Purkar at IIT Bombay in 2018. So after that, he moved to Cornell University to work with Professor Dan Ralph and Professor Robert Berman in the field of spin orbitronics and spin caloritronics. He has done a wonderful PhD thesis at IIT Bombay and actually got the best PhD award from IIT Bombay in 2018. And as I heard that he's soon moving to another interesting group, Professor Matthias Chloe. And I really wish Arnab a bright career. And I'm very happy that he's going to give a lecture on his recent work on iridium oxide and similar stuff. So with this very little introduction, I welcome again Arnab to this webinar and welcome you all. So I just request that during the lecture, we don't take any questions. If you have any questions, please write in the chat window. And after the seminar, we will take questions one by one. So Arnab, all yours. Looking forward to your next lecture. Thank you.
Thank you, Professor Vedanta, for this nice introduction. It is my pleasure to present in this occasion. So I'll be presenting the work that I have been doing in Cornell since last few years. Mostly this is related to spin orbitronics and some part of spin caloritronics. So the outline of my presentation is the following. First, I talk about the spin orbitronics, spin orbit torques generated by direct nodal line iridium oxide semimetals. So in this work, we show the direct correlation of direct nodal lines on spin Hall conductivity. Next, we study the spin orbit torques, particularly unconventional spin orbit torques in ruthenium oxide. The main focus is that how the Niels ordering and antiferromagnetic ordering controls spin orbit torques. And after that, I talk about the spin kind generation by driving thermal gradient from spin Nernst effect. And I discuss the various origins of transverse thermoelectric voltage that can be originated in ferromagnetic insulator heavy metal bilayers. And after that, I'll just briefly outline some of my PhD related works. So without wasting much time, let me start for the motivation of iridium oxide. So there is plenty of motivation to work on iridium oxide. First of all, it is a direct nodal line semimetal. So direct semimetals are 3D analog of graphene where conduction and valence band cross at a single point in momentum space. So for that, crystal and time reversal symmetries will be preserved. In addition, if we have other sort of symmetries, such as non-symmetric symmetry, then instead of having one point in momentum space, it can have multiple crossings forming line or forming arc. So 2018, it was predicted that iridium oxide, ruthenium oxide, osmisium oxide, various rutile oxide would host direct nodal lines. And there are different types of direct nodal lines, type 1, type 2. And based on the location of these direct nodal lines and position of them and type of them, it can actually contribute to spin Hall conductivity. So recently, our collaborators are able to grow iridium oxide in the thin film limit down to 5 nanometer by doing MBE. And they have shown they have shown the existence of this type 2 direct nodal lines in these films, in this MB grown films down to 5 nanometer. So this actually sets a nice platform for us to study spin orbit torques in this material and to know whether direct nodal lines play any role in determining spin Hall conductivity. So since this is thin films, they are grown on single crystal titanium oxide substrate, 001 oriented or 101 oriented films. So when it is grown on 001 oriented films, they are uniformly strained, and this strain is quite small, about 2%. When it is grown on 101 oriented films, it is highly strained, and it is quite asymmetric. That means two different directions of iridium oxides have two different strain. That immediately suggests that this non-symmetric symmetry would be broken for 101 oriented films. Now, so there is some rule of thumb that we can quickly know how from the band structure, how spin Hall conductivity can be determined. First of all, we need to know whether we have band crossing near the Fermi energy level. So without considering the spin orbit interaction that is shown here. Next, we have to consider the spin orbit interaction and do the same DFT calculation and see if there is any band gap opening near the Fermi energy level due to spin orbit interaction. So this is known as band anti-crossing. So if the number of band anti-crossing is more, so the material will have high spin curvature. So we did some DFT calculation for this trained film, and we found that without the spin orbit interaction, actually band crossing takes place quite away from the Fermi energy level or quite away from the previous unstrained iridium oxide. So 15 to 20 milli electron volt shift is quite significant. Secondly, without the spin orbit interaction previously, it was 6-fold degenerated. But now, because of strain, because of this anisotropic strain, this degeneracy is broken, and now it is fourfold degenerated. So we have band gap opening due to strain, but not due to spin orbit interaction. So this together should actually decrease the spin Hall conductivity for 101 oriented films. Okay, so this is the argument, but we need to see experimentally what happens. So for that, we studied this set of samples, permalloy grown on iridium oxide. And sometimes we have iridium spacer between permalloy and iridium oxide. So we have iridium spacer. The reason is that when we try to grow permalloy by sputtering on iridium oxide, actually permalloy pulls, particularly iron atom pulls some oxygen from iridium oxide, which is confirmed by the yield study with the data I'm not showing here. You can refer to this paper. So, this happens quite a bit for 001 oriented films, because the uncoordinated oxygen atom density is more for 001 oriented films. So if we have interfacial oxidation, that will make the interface bad. So to avoid that situation, we have inserted very thin iridium spacer. Okay, so now let's talk about measurement technique. We did very standard Pintor ferromagnetic resonance. We have devices patterned into coplanar waveguide structure. We run RF current and measure DC voltage, because this RF current will create various types of torques on the magnet, and it will drive the magnet into resonance. So oscillatory magnetoresistance and oscillatory current will produce a DC voltage. So this is typical DC voltage spectrum that we observe in this system. So first thing that you'll immediately notice that the voltage spectrum is distinctly different for 001 plane compared to 101 oriented planes. That immediately suggests that something fundamentally different happening in these two planes. So we have adapted this method as developed by our former group mates to quantify spin orbit torques. So it basically tells that we have to measure this zeta FMR, the efficiency of FMR, which is determined by the ratios of symmetric and antisymmetric Lorentzians and some other thickness, other values. And we have to plot this against the inverse of the ferromagnet thickness. So from this, we can quantify the damping like torque efficiency. So if you plot this, the inverse of intercept will give us the damping like torque efficiency, and the from slope will get the field like torque efficiency. So let's now talk about the results. So first, I'm showing the data for the without iridium spacer one. So you can immediately see that the two different directions of 101 oriented planes have two different values of spin Hall conductivity and spin Hall angle. So it varies from 12 to 18%. So about 50% difference in spin Hall angle. Okay, just to remind you that this 101 oriented film was anisotropically strained. Now, when we have iridium spacer inserted, then actually this number goes down to 5% and 8%. So this reduction of damping like torque efficiency is expected. Basically, it tells that some amount of spin current is lost while it is transported through the iridium spacer. And from that, the calculated spin diffusion length is about 1 nanometer. This is also consistent with this recent experimental study. So this is all standard with some difference or with some anisotropy in spin Hall angle. But very dramatic thing happens for 001 plane. So we expected it should go down, but it increases quite a bit, almost by factor of 3 when iridium spacer is inserted. So this basically suggests that previously I argued for 001 plane, the interface is bad when parmala is directly deposited into it because of the interfacial oxidation. So the moment we have iridium spacer, at least the interface is good, magnet is not oxidized, so we can probe the bulk spin Hall effect. This is to remind you, even for this, we have significant spin loss through iridium. That means the bulk spin Hall angle of iridium is even more than that. So if you want to compare everything in one platform, let's compare everything when we have iridium spacer inserted in all. So here you can clearly see that for 001 oriented film, the damping like torque efficiency is almost 1 order magnitude higher than the 110 oriented films. This clearly suggests the importance of the direct nodal lines. Those were present in 001 oriented planes. And this clearly indicates that for 101 oriented planes, the band anti-crossings were happening much away from the Fermi energy level, and direct nodal lines were disrupted. So hence, this work clearly demonstrates the correlation between the direct nodal lines and spin Hall conductivity in this kind of topological materials. So far this is the room temperature data. We have also done temperature dependent study. So we calculated the damping like torque and field like torque efficiencies as a function of temperature. So we know how materials resistivity changes. And if we know the resistivity and damping like torque efficiency, from that we can quantify the effective spin Hall conductivity. Effective spin Hall conductivity means this is the lower bound because the interface transparency is always less than 1. So if you convert everything into effective spin Hall conductivity, then we see the distinct regimes of spin Hall effect in the same material. For example, for 110 oriented films, we see that the effective spin Hall conductivity is nearly constant, almost independent with respect to the electrical conductivity. That is what people would expect for a clean metal regime. And for a dirty metal regime limit, actually it should linearly increase that we see for 001 oriented films. Just to remind you, 001 oriented films resistivity is over 200 micron centimeter. So in general, it should belong to dirty metal regime limit that also we experimentally verify. So various regimes of spin Hall effects were predicted in various papers, which we nicely observe in a same material when they are grown into different planes or to different substrates. So this work finally summarizes the follows. We can correlate the relation between spin Hall conductivity and direct nodal lines, and also we observe different regimes of spin Hall conductivity. So after that, now I talk about there could be some unconventional spin orbit torques that can be allowed by the symmetry. First, let's start with the basic spin torques. So this is typically happens for standard heavy metal ferromagnet bilayers, where we have spin orbit interaction or Rashba kind of interaction. This basically tells that in-plane current will produce in-plane spins perpendicular to the direction of charge current, and that will flow perpendicular to both of them. So this can produce both damping-like torque and field-like torque. The requirement for this kind of conventional torque is that we need a material which has high which has high spin orbit coupling, such as platinum, tantalum, iridium oxide. So there can be some materials where crystal inversion symmetry is broken, and it may have Russell-House interaction. In those kind of systems, if you run current in certain crystal axis, then you'll see that spins polarized along the direction of charge current will be accumulated at the interface. Again, those accumulated spins can produce damping-like torque and field-like torque. So these kind of things are observed particularly in the semiconductive systems like gallium manganese arsenide kind of materials. Now, very third type of spin current generation is possible, which is strictly allowed in low symmetry material, where out of plane spins are created from in-plane charge current. And these out of plane spins again can create out of plane anti-damping torque or in-plane field-like torques. So this is very interesting. The reason is that it can actually switch out of plane magnet, which doesn't need any in-plane symmetry breaking field. So out of plane magnetization switching is important for high density memory applications. And secondly, origin of this kind of spin torque is not very well known. So this is very interesting to understand from fundamental perspective as well. Now, question is that how do we know all 6 types of spin orbit torques experimentally? How can we distinguish them? So there is an easy way. We can do angular dependent STFMR, or we can do angular dependent second harmonic method. So I have already introduced STFMR and told that it produces symmetric and antisymmetric Lorentzian. So we can set magnetic field defined angle with respect to the current and get a symmetric and antisymmetric as a function of phi, the in-plane angle between current and magnetization. So from angular dependence of them, we can actually quantify all 6 terms. So here for simplicity, I have shown 3 terms. So this component shows damping-like torque from spin Hall effect, and this component shows the out of plane. This shows actually there is some mistake in this equation. So by the way, the basic principle is that by fitting this into this kind of expression, we can actually quantify all 6 spin orbit torques by doing STFMR. And also similar thing is possible when we do the second harmonic analysis. Okay, now question is that what is the requirement for these unconventional spin orbit torques? The first point is that it should break the twofold rotational symmetry. Let me give you one example. Let's consider this material where current is flowing in this direction. And if we assume that out of plane spins are produced, that means if we take the mirror reflection, it flips the sign. Out of plane spins flip the sign. Current doesn't flip the sign. but this is current-induced phenomena. That means material has to flip the sign. That means the material symmetry has to be broken perpendicular to the direction of current flow. One classical example is the WT2 tungsten telluride that was reported previously by Dan students. So this was one example. Uh, it can be broken in another way. For example, if we have some magnetic moments in the spin current generator, so the magnetization parallel to the direction of current, then also it breaks symmetry. So in this kind of systems, we can also observe this kind of extraordinary spin orbit torques. So in that search, we found that ruthenium oxide is a material very recently collinear antiferromagnetism is discovered. And it was also not predicted. So it was a surprise discovery. So previously there was a lot of excitement with non-collinear antiferromagnets, and it was theoretically proved that non-collinear antiferromagnetic ordering can produce different sort of spin orbit torques. But there was no theoretical prediction or experimental demonstration that collinear antiferromagnet can do such thing. So this is one example. Second thing is that ruthenium oxide. So recently our collaborators have shown uh, strain stabilized superconductivity in ruthenium oxide. Third, ruthenium oxide also has direct nodal lines. So direct nodal lines with antiferromagnetism is also very exciting. And also, since it has collinear antiferromagnet, and even though bulk ruthenium oxide is centrosymmetric, but the ruthenium atoms along with two adjacent oxygen atoms are non-centrosymmetric. And based on that, there are a lot of recent theoretical predictions that it could produce unconventional spin orbit torques. So there is plenty of motivation for single crystal ruthenium oxide. So we started to look at what happens for this. So we studied 101 oriented ruthenium oxide. Here I show the data for the second harmonics. So previously I discussed about the STFMR. Now I'm showing the data for second harmonics. So you can easily see the difference between these two curves. So these two curves are obtained when current passed into two different directions of 101 oriented ruthenium oxide film. So when it is passed in 010 direction of 101 oriented films, we see a lot of unconventional out of plane anti-damping torque. But we don't see that when it is passed in the other direction. Now question is that what is the origin of this unconventional spin orbiter? Is it a bulk? Is it arising? Is it a bulk spin current, or it just arises from the crystal structure of 101 oriented plane? So we did control experiment on iridium oxide 101. The reason is that iridium oxide and ruthenium oxide have almost similar crystal structure and very close lattice constants. But we don't see that kind of extraordinary out of plane anti-damping torque from 101 oriented iridium oxide. So at least we can tell that it doesn't arise from the crystal structure. So there has to be something different. So very recently, we found in our squid measurement the inverted hysteresis in ruthenium oxide permalloy in this kind of samples. Inverted hysteresis means generally what happens, forward loop comes as shown here, and reverse loop comes later. But in this kind of materials, we have inverted hysteresis. So forward loop comes earlier and reverse loop. So this is known as inverse hysteresis. So this typically happens in systems where antiferromagnetic coupling is present. So we suspect that this antiferromagnetic coupling is the mechanism for this out of plane anti-damping torque, as it can break the mirror symmetry. So to know whether it's interfacial or bulk effect, we have inserted some spacers such as copper or iridium, and we confirm that when we have this kind of spacer, we don't observe this kind of unconventional spin orbit plots. So from these experiments, we confirm that the antiphenomenon coupling at the interface can break the symmetry and produce unconventional out-of-plane anti-damping kind of torques. So this is our ongoing project. I'd like to finish this ruthenium oxide
Hello, Arnab. I think we lost Arnab. Is it me lost everyone or we just?
No, I can't hear him as well.
Okay.
Even we cannot hear you.
Okay. So I think Arnab has some issues, and I'm sure he will come back. So kindly stay tuned. Sorry for the inconvenience. Yeah. So he has logged out. Probably will join soon.
Hello, everyone.
Oh yeah, good to have you back. Okay, let me make you again.
So I exactly don't know at what stage.
Okay, you share your screen. We'll tell you.
Okay. Are you able to see my screen?
Yes, yes.
So
Yeah, I think. Yeah, on this screen, you are almost finishing this
okay.
unconventional hysteresis loop. So
Okay.
maybe you just get back to that and continue.
Okay, so yeah, that's what I had for now on ruthenium oxide. So I now discuss about the other possibilities. What are other sources to generate spin currents and spin orbitals? So far I have been talking about the charge current to spin current conversion by spin Hall effect. So due to Morse relation, so its thermal analog is also possible. That means if we create thermal gradient, that can also produce transverse spin current. So this is known as spin Nernst effect. So we study this in TMIG. TMIG is a ferromagnetic insulator, TMIG tungsten kind of bilayers. So we measure the Hall voltage and Hall resistance. So it can be derived in two ways. So one is that ρ2, which is associated with the out of plane field sweep. So it will give the AHE-like signal, and the next term is ρ3, which will have a similar symmetry as PHE. But this originates from spin Hall magnetoresistance. So another point to note is that for ρ3, we have direct spin transmission, and real part of spin mixing conductance comes into the expression of ρ3. Whereas in ρ2, the imaginary part of spin mixing conductance comes into the picture. So first, I show the results of the electrical data. When we run electrical current, we see standard hysteresis because this is a PMS sample, perpendicular magnetic sample. So this is all standard. Now, instead of running electric current, we create thermal gradient. Here I have shown the device for that. We have heater and one device between two heaters. So when we run thermal gradient, again, we see very nice thermoelectric transverse voltage. So this corresponds to the thermal ANE kind of data. but originating from spin-Nernst effect. So this is also quite expected. But the difference is that if you take the ratio between AHE and PHE and ANE by PNE, they don't match. So they're quite different. Now, question is that if the mechanism is spin current, then this should have been same, because it will depend on the interface and it will depend how much spin kind is generated. So how much spin kind is generated, if that is determined by spin Hall effect or spin Nernst effect, and if the interface does not change, so they have to be same. Okay, so this is not first time we have observed. The first observation was from MIT group. So they reported TMIG platinum, then the discrepancy was even more. It was like 10 by 1.5. So according to them, it cannot be explained by spin Nernst effect. So there has to be something. So they call it spin drag mechanism. So what it does, so when we have thermal gradient, in-plane thermal gradient in this kind of system, it by default has out-of-plane thermal gradient. Since this is a PMA magnet, so this out-of-plane thermal gradient actually injects out-of-plane spins. So when these spins are dragged along the direction of in-plane gradient, it actually deflects sideways because of the inverse spin Hall effect. Because when platinum carries charge current, it produces spin current in the transverse direction. So this is the extra source for this anomaly. This is how it was explained. But the problem is that if it is a source, then the transverse voltage should be proportional to the in-plane thermal gradient and out-of-plane thermal gradient. Generally, these in-plane and out-of-plane thermal gradients are proportional to the heater power. So we should see. Oops. So we should expect that that the transverse voltage should depend on the square of the heater power. But for this experiment, we see very much linear dependence with the heater power. So we believe that this thermal drag model is not 100% correct. So it has to be, there has to be something else. Okay, so we try to know the thermal gradient in this system. The way we know the temperature is that when we do the experiment and create thermal gradient, we measure the resistance of the device. So as it becomes hot, its resistance changes. So from the resistance of the device, we exactly know the resistance as a function of distance. So from that, we get the temperature profile. So the typical thermal gradient is about 1 to 2 Kelvin per micron. So the important thing that we notice that when we try to create more and more thermal gradient, actually base temperature, the overall temperature also increases. So for the maximum thermal gradient, when we try to create, the temperature is not room temperature, it is almost more than 100 Kelvin. So that means temperature dependent thing we have to take care of. So we measured the temperature dependent PHE and AHE, and we see quite significant variation of PHE and AHE as a function of temperature. And if we take the ratio of this PHE and AHE, they actually fall. That means when we need to compare ANE by PNE, so for the maximum heater current, when we are doing ANE PNE by ANE, we are actually doing at 417, above 400 Kelvin. So we need to compare PHE by AHE, not at room temperature, but at this temperature. If you compare them, their number becomes almost same. So that means we explain this data not with the thermal drag model, but with the temperature dependent variation of real and imaginary part of spin mixing conductance. However, I have not shown this data, but we have verified that magnetic proximity effect is negligible in TMIG tungsten. So it is a very clean system. So we also want to compare this, what happens for TMIG platinum. So, but when I did TMIG platinum, result is very surprising. So again, this is the AHE and PHE data for TMIG platinum, very similar to TMIG tungsten. And also this is the thermal analog of that. This is also similar. Now, if we take the ratio of this PHE Is there any question?
Good morning, everyone.
Good morning, ma'am. Good morning.
Yeah, please.
Others, please mute your microphone. So I don't know who is this person. Ranjit K. Okay, I mute him. Okay.
Okay.
Everything is under control. Please continue.
Okay, yeah. So if you take PHE by AHE for TMIG platinum, then the ratio for electrical one, it is, if you do even temperature dependent, it varies between 40 to 20. And if you do PNE by ANE, then it is around 0.5. Now, if you compare PHE by HE and PNE by ANE, it is 40 divided by 0.5, which means about 100. So discrepancy in TMIG platinum is huge. So even this cannot be explained by the temperature dependent PHE by AHE term. So that means the way I explained the data for TMIG tungsten, by the same way I cannot explain the data for TMIG platinum. And also it cannot be explained by thermal drag. Again, I have shown that the Hall voltage is linear. If it was due to thermal drag, it should have been proportional to the square of the heater power. And secondly, if it was due to thermal drag, then PNE by ANE should also decay as a function of the spacing between heater and the device, but it is almost constant because the outer plane thermal gradient decays way faster than the in-plane gradient. So the way we analyzed the data for TMIG tungsten, same thing cannot be explained. So there has to be something else. So when we try to find that, we found very strong magnetic proximity effect in TMIG platinum. So we so from this marks, so we can get the numbers of PNE and ANE from this proximity effect. So PHE, the way PHE and AHE scales electrically, PNE and ANE may not necessarily scale due to the thermal gradient because of this fact. The original mechanism behind PHE and ANE or AHE are different. So they have different origin, different types of spin orbit coupling. So this prefactor lambda and gamma, they are different. And also, so if you convert this expression into this, then ANE and PNE would convert into this. So it will depend on the energy derivative of this lambda and gamma. So these values are not necessarily to be same. So the final point of this is that, so in a material where we have PHE and AHE, so we have PHE and AHE when we run electric current. And from that, we cannot just simply say that it will scale in a same manner when you run thermal gradient. The reason is that the reason behind this is the temperature dependent lambda and gamma. Sorry, temperature derivative of lambda and gamma, and also the values of N and M. So we believe this is the reason behind the deviation of AHE by PHE and ANE by PNE for TMIG platinum. So so we know the proximity, whether we have proximity induced effect or not, by rotating magnetic field into different axes as shown here. So from this, we know whether the material has magnetic proximity effect or not. So in conclusion of this work, we see the difference in ratios for PHE by AHE and PNE by ANE. And the ratio between them for TMIG tungsten is nearly 3, but same ratio becomes almost 80 for TMIG platinum, and previously it was reported 8 to 10. So the way we are explaining this, TMIG tungsten film is more clean because it doesn't have magnetic proximity effect, and that's why the deviation is small. And whatever deviation we observe, that can be simply explained by the T-dependence of GI, real and imaginary part of spin mixed conductance. Whereas For TMIG platinum, the interface is already proximatized, and we have large deviation in PHE by HE and PNE by NE, and only spin Nernst cannot explain this. So interface-induced proximity effect is needed to explain this data. However, in all these cases, we don't find any evidence of thermal spin drag mechanism which was proposed by the previous, which was proposed in the previous report. So with this, I conclude my presentation. With this, I conclude my work that I have been doing in Cornell. So I'd like to thank many people, Josing, who had worked with Professor Shen in Cornell University. So we thank Xiao and Professor Muller for doing TEM images, and also Priyam Bhattacharjee to do the DFT calculations for Iridium related work. So I'm also thankful for to Hari, Net, and Jackson for the growth of Ruthenium oxide. They have been working under Professor Shlom in Cornell University. Also, we are very thankful to Professor Caroline Ross from MIT for providing us TMIG films, and his student Jackson, Jackson Bauer for the growth. It is ironic that previous paper on TMIG platinum was only by them, and now we are contradicting with their previous result. Also, we like to thank Professor Nitin Samarth and Richard L. Love for providing bismuth, selenide, and antimetallite samples. And also, we are thankful to Professor Yang from Ohio State and his student Jason for growing some in-plane films where we did some non-local experiments. Finally, I'd like to thank Professor Dan Rolfe and Professor Robert Berman for their support over the years, and also our group mates for their help. So I'm about to finish. Just before I finish, I like to explain. I like to discuss a little bit about my PhD related works. So there we have reported the first, not first, but one of the first experimental evidence of thermal spin torque in magnetic tunnel junctions, while we see the shift in the hysteresis loop when we create thermal gradient. So after that, we also shown spin Nernst effect by doing a different sort of experiment. This work was highlighted in the cover page of APL that time. So we also observed the evidence of spin Nernst torque. So this was the first experimental evidence in spin Nernst torque reported 2018. So I like to encourage you to go through this recent report published from Korea. They have also reported spin Nernst torque in tungsten perpendicular coffee bean systems. Also, we have reported that time the anomalous spin orbit torque generated in magnetic trilayers. This is also very similar to ruthenium oxide. In ruthenium oxide, we are claiming out-of-plane anti-damping torque. But here in this work, we claimed that an out-of-plane effective field can exist. So this is also comes into the unconventional spin orbit torques. So we did experiments in chromium-based system where we found that the thickness of chromium plays very important role, and there was some transition as we change the chromium thickness, probably some phase transition. Chromium becomes very highly resistive, and in high resistive phase, it used to produce very large damping like torques. So also, chromium has some antiferromagnetism, so we could not quantify that time whether antiferromagnetism was related to this or not, but that was a good question. Also, we have shown that an improved measurement of DC bias STFMR. So the standard way to measure DC bias STFMR is that just run DC current and measure the longitudinal voltage. But here we showed that if you measure the transverse voltage, measurement would be very clean and data would be very accurate. If you do the longitude, the trivial one, the data is generally hopeless and people often report very wrong number. So I'd also encourage to have a look on this paper recently published from Dance Group. So they have actually done a little bit more on that, and in this work they have shown that spin pumping signal can also be separated from the spin torque signal by comparing the longitudinal and transverse voltage STFMR. So with this, I like to conclude my talk, and also thank my PhD supervisor, Professor Tulapurkar, also my PhD colleagues for their support over the years. So thank you. I can be able to take questions from now.
Okay, thank you, Arnab, for this excellent lecture. So I clap for you.
Thank you.
Really nice overview of many subtopics. So can we have some questions? Let me see in the chat window. There are no questions yet. So let me just give a head start. So on this TMIG tungsten, you said there was no proximity effect, but in the TMIG platinum, there was proximity effect. So what could be the reason behind it?
So that is very tough question. So I don't have a clear answer for it, but even previously people have talked about various possibilities that platinum is more susceptible to become proximatized. Even when spin Hall magnetite resistance came, people even that time also talked about magnetic proximity effect. So exactly, I don't have any answer why tungsten is less susceptible, but it is more or less a fact that platinum is more prone to magnetic proximity effect.
Oh, sorry, my microphone was on. So I was asking, how do you know that there is a proximity effect?
Yeah, so actually, I was supposed to put the data, but I forgot to put the data. So I have put the data for TMIG tungsten, but I forgot to put the data for TMIG platinum. So basically, you can do the best way that I feel is that you can measure SMR while rotating magnetic field out of plane along the direction of current as shown in figure B and perpendicular to the direction of current as shown in figure C. So if the magnet is insulator, then in this configuration B, you should not see any magnetic resistance, because in figure B, the magnetization and current, the angle between magnetization and current continuously changes. So it basically gives you AMR. So if the magnet is pure insulator, then it should not produce any AMR. If it produces any sort of AMR kind of signal, that immediately implies that there is a bit of conducting magnet, and that bit of conducting magnet is due to the proximity effect at the interface. So this data is for tungsten, and the red curve is the AMR, where we don't see any significant proximity effect. So we conclude that TMIG tungsten has negligible proximity effect. I wish I could show the TMIG platinum. Actually, TMIG platinum has severe proximity effect.
Okay. All right, there are some other questions. Let us go to that. Sobhik, please ask your question.
Hi, Arnab. It's a great talk. So I was just curious about the first part of your talk about iridium oxide. If you go back to the data, yeah, where you were showing that you expect the Dirac line node on the O1 and not the other one. But I thought you have similar, like where you have the spin Hall conductivity data. But it seems like you get similar spin Hall conductivity for both your 001 and 11 oriented. Like if you go.
No, the conductivity is not similar. So conductivity is also quite different. So
If you
this
go
is the, so there is a prefactor of 10⁵ multiplied with this. So spin Hall conductivity is a parameter which is significantly different between these two.
Oh, so that data is then not correct, is it? If you go to the left table.
Here.
Yeah. So you say 1.95, right?
Yeah. So 1.95 10⁵ is for 001. Oh, so no, here you should compare with this. Oh, this data is, I'm sorry, yeah, this is incorrect. Yeah.
Okay, so it is in
yeah.
fact much
Yeah.
reduced.
I'm sorry, yeah, I mean, it's a typo. So basically, this data is, it is, this should be this value, 0.78. Yeah.
Great.
I mean, this is a very good point that you noticed and asked. Yeah.
No, okay. So about the, for like when you use the Iridium spacer, I guess the Iridium was grown in MB, right?
No. So I got the Bearsoon, so we did that by sputtering.
Okay, but you still have then like some, so your whole idea is that the Iridium in contact with oxygen is much more stable than
right.
permanent.
So as you know, Iridium, platinum, these are the materials which don't like to get oxidized. So yeah, they are pretty novel, Iridium, platinum, gold. So you know better than me how to make this oxide novel materials. And
okay.
there are tricks too, yeah.
Okay, great. Thanks.
Yeah.
Okay, so do you have more questions?
No.
Okay, thank you. Abhirup Dey. Abhirup, please ask your question.
Yeah, it's a nice talk. I enjoyed the talk really. I have a couple of small questions. One is at the TMIG tungsten. Yeah, I think the third part. Can you just go there? Yes. Here. Okay, fine. So okay, the back slide, the TMIG, the first slide.
I'm sorry. Yeah.
This one.
I'm sorry. Yeah. It is the one.
This one. Okay,
yeah.
It's fine. So the only thing, just one small curiosity is that why these hysteresis loops looks different and coercivity field.
That's a very good. Yeah, that's a very good question actually, and that's a very nice observation. So here I have shown only one data for one heater power, and also it happens because the overall temperature increases. So here I have mentioned that for the maximum heater power, when we try to create the maximum thermal gradient, the temperature is around 400. And as you increase the temperature, hysteresis loop goes narrow and narrow.
Okay. It's a different effective temperature shifted actually.
Yeah.
Okay, and another one where you check the next some slide where do two different types of rotation, gamma and alpha, what you say, along the current and orthogonal to the current. The rotation to check the proximity effect.
Oh yes, yeah. Here.
Yeah. So my curiosity is that this is all in thin film form, right? A very when the layer by layer is on in device. So is there any role of weak anti-localization type of thing? Even copper can show such things.
So yeah, I mean, magnetic proximity effect means that if a non-magnet
apart from proximity, I mean the copper can also show this anti-localization type of thing, not about the proximity induced magnetization, but
so in that case I don't know whether that will show this kind of angular dependence. They have a specific angular dependence of cos square theta.
There are people telling with like Hanley magnetoresistance and wall, where the magnetoresistance scale above the saturation magnetization, then the field dependent study probably required.
So yeah, in that case, I cannot comment whether it will follow the proper angular dependence or not. So yeah, even in tungsten telluride kind of films, yeah, this is a valid point that people have reported extraordinary magnetic resistance, and probably that also goes with cos squared theta dependent. So yeah, that sort of thing can analyze.
But then this along the line rotation, how it reflects over there? I mean, if it is not at all from the proximity, something else, if there.
So now question is that if it is from something else, so we have to know what could be that reason. So there, so the way people, when people talk about it, they sometimes insert some spacer and show that when you have a spacer, you don't see it, and when you don't have a spacer, you see it. That means the interface between these two is important. And also there can be other ways to check by doing MCD kind of things. And also if the magnetization directly can be measured precisely, doing speed or something else, that bare TMIG and TMIG platinum. So yeah.
Okay, okay, fine. This are small two things. Okay.
Yeah,
Maybe
but that's a good point.
Sorry, maybe I can make a quick comment about the weak localization, anti-localization. These are generally low temperature physics. So this is, I guess, room temperature, right?
Yeah.
So I think one can safely rule those out. Okay.
Yeah.
Okay, I have one question. Oh, okay, Ashwin has a question. He gets priority. Please ask your question, Ashwin.
Thanks, Arnab, for the nice talk. I have one question on the iridium oxide. So these are single crystal films, right?
Your voice is
Along
breaking.
which direction you flow. So this iridium oxide are single crystal films, right?
Yes.
Hello, can you?
Yes.
So does it? So when you measure the STFMR, does it matter along which direction the RF current is flowing?
Yes. Absolutely. Yeah. So actually, it depends. Okay. First thing is that 001 plane is quite isotropic. So two different directions of 001 plane produce almost similar result. But 101 oriented film is quite anisotropic. Two different, I have not shown everything in details, but two different directions of 101 oriented film also has some anisotropy in spin Hall angle and spin Hall conductivity. So there is also anisotropy in spin Hall angle in two different directions of 101 oriented films.
Okay, so for 001, there is no anisotropy. You're saying it is same spin Hall angle.
Yeah. So the original theory paper actually predicts the precise angular dependence of spin Hall. I'm sorry, the precise crystal axis dependence of spin Hall conductivity. But in this work, we exactly cannot. I mean, we could not observe the same thing, but we could see very drastic difference between two planes. So in that way, we are saying that the Dirac nodal lines are playing important role.
Yeah. Okay, thanks.
I have a very quick technical question. So these iridium oxide films, you deposited on titanium oxide. Titanium oxide was the substrate, or it was just another thin film, like a buffer layer, sheet layer?
Oh, titanium oxide is a substrate.
Okay, it's a substrate. Okay.
Yeah.
All right. Good. Very good. So any other questions from anybody? I do not see that case. So then I think we can summarize now. So very nice lecture detailing a few important topics in Spintronics. So we thank Arnab Bose for this excellent lecture. And next week will be, it will be who actually? Ruslan Nikolic. Yeah, so Professor Ruslan Nikolic from University of Delaware. Yes. He will be giving lecture. next week. So see you. But next week the lecture will be at 10 a.m. So because he's from US and he preferred 10 a.m. Otherwise there is a lot of time difference. So see you next week then. So we clap again, Arnab, for you. Thank you so much. So all of you,
Thank
please
you.
get there and see you next week. Bye bye.
Bye bye.